So this leads us to an understanding, better understanding anyway, as to exactly what a liquid is. Now we know that liquids are a little higher kinetic energy than solids and less kinetic energy than gases. But we do know that liquids have pretty strong intermolecular forces. We also know that liquids are almost incompressible, like you can't force them to take on a different volume. This is the same for solids. Now with gases, it was really easy. You could pressurize them, shrink them down, pressure and volume inversely proportional, all that kind of jazz. When you have a liquid, if you add enough energy, you can break those intermolecular forces and form a gas. That process is called evaporation, and it's probably a term you've heard before. Liquids going to gas, you need to evaporate the liquid, but you have to add you have to add energy to it, all right? It breaks the intermolecular forces between the molecules. If you have a gas and you cool it down, you're essentially taking away a lot of the kinetic energy. And when the kinetic energy is removed, the gas can no longer fight the intermolecular forces. So intermolecular forces are always ready to form. That process is called condensation. If you take a gas and you condense it down to a liquid, that's condensation.
Molecules of a liquid have a range of kinetic energies. Some have enough energy to overcome intermolecular forces. If these high-energy molecules are at the surface of the liquid, they can escape into the gas phase. This is an endothermic process.
So notice that it takes energy to turn a liquid into a gas. So turning a liquid into a gas is endothermic. You have to add energy to make it happen. Maybe it's energy from the sun. Maybe you put this on the hot plate at home on an oven or something like that. But you have to add energy. And what's also fascinating here is that if you want to have a gas turn to a liquid, you're actually going to remove energy. So if one direction of a chemical reaction is endothermic, the opposite direction is almost always exothermic. So going from a gas to a liquid, i.e. condensing a gas, exothermic. So start thinking about this as we go through these new sections. We saw in the gas law section that there is an average speed or an average energy of gases, but some of the gases will be really slow, some of them will be really fast. It's an overall average that we're looking at. And we looked at graphs kind of like the one there on the right-hand side, where there was like a top to the little peak, and the tops of these peaks, like right there and right there, those would be the average value, all right? In this case, average energy. Well, liquids do the same thing. They have an average energy, which I just highlighted there with my pen, but there's going to be ones with less energy and ones with more energy. And it doesn't matter the temperature. So the blue line is the colder temperature and the red line is the warmer temperature. So you still have cold molecules in both, and even at the colder temperature, you have some warmer molecules. But what's different here is that in this graph, we have this dotted line, and that dotted line, it represents the minimum energy needed to break those intermolecular forces and evaporate the liquid. And so at the warm temperature, you have a lot more molecules able to evaporate. Everything to the right of the dashed line that's below the red line, all of those molecules are capable of evaporation. But everything to the left is not. So when you boil something, it's a gradual process. It doesn't just all of a sudden like turn to a gas. You start to have things evaporate, but it takes a while. But what's really wild is that the blue line, the lower temperature, even that has some molecules down there, which I just kind of scribbled on. Even it has some molecules that have enough energy to break the intermolecular forces and evaporate. And this little tiny bit of energy at the cold temperature and the big amount of molecules at the warm temperature, this results in what's called vapor pressure. And all liquids have a little bit of gas molecules above them, all right? Molecules that were able to escape the liquid and turn into a gas, and gas molecules have pressure. So vapor pressure is just so much liquid that has evaporated. It's a little bit of gas over the liquid. The vapor pressure will increase as your temperature increases. You keep adding energy, and more molecules are able to evaporate. And then finally, you'll get to some point where all the molecules have enough energy, or at least almost all of them, and you have evaporation, true and simple.
In a closed container, molecules move back and forth between the liquid and gas phases. If the rates of crossover are equivalent, the overall amount of substance in each phase remains constant. The system is said to be in a state of dynamic equilibrium.
The liquid in the butane lighter is in dynamic equilibrium with the gaseous butane, which has a vapor pressure of about 2.4 atmospheres. When the valve is opened, butane gas escapes from the lighter, the system goes out of equilibrium, and liquid butane rapidly evaporates into the gas phase. When the valve is closed, the system quickly comes to equilibrium again, with the pressure of the butane vapor equal to 2.4 atmospheres.
So this vapor pressure thing is really cool for chemists. If you have a flask, like the first video that was shown, and that flask has a lid on it, then above the liquid, you're always going to have a little bit of vapor pressure. And again, vapor pressure is just some of the liquid which has enough energy to turn into a gas. And if it's a closed system, then some of the liquid turns into the gas, but some of the gas turns back into the liquid. So once after it establishes itself, which often doesn't take too long, then the rate or speed of evaporation, liquid going to gas, is equal to the rate or speed of condensation, gas going to liquid. So these molecules are going back and forth, back and forth, back and forth, if it's a closed system. And this process is used in the cigarette lighter there in the lower right-hand corner. And I'm sure you don't smoke, ha ha ha. You use these for rock concerts, ha ha ha. I need to have a day job. But anyway, I have a day job. Okay, I need a... Profat back on. A butane cigarette lighter initially has a closed system, and that butane, which is the liquid you see usually in the cigarette lighter, has a vapor pressure over it, has some gas. So when you open up the cigarette lighter, a spark forms, and the spark ignites the butane. Butane is a compound, it's like a fuel, and it creates CO2 and water, but it does create a lot of energy. And so you do whatever you do with the cigarette lighter. Eventually you close it, the equilibrium reestablishes itself between vapor pressure, the condensation and evaporation, and then you're good to go. After a while, if you use your cigarette lighter a lot, it gets low. But once in a while, when it's really low, you can still get a flame because there's enough gas inside there to have a little bit of cigarette lighting capability. Kind of fun. Anyway, vapor pressure is nothing more than a pressure. So we'll use millimeters of mercury, we'll use atmospheres, millibars, all those things we used in the gas chapter to measure it. But again, remember that all liquids will have a little bit of vapor pressure over them, which is kind of interesting.
As heat is added to a beaker of water, the vapor pressure of the water increases, thereby increasing the rate of evaporation. If enough heat is added, the vapor pressure of the water equals the atmospheric pressure. At this point, large bubbles of vapor begin to form in the liquid, and the liquid boils.
Boiling, the act of boiling a liquid, is when the vapor pressure of the liquid, above the liquid, equals the atmospheric pressure. So in the upper right-hand corner there, notice that there's a dashed red line at 760 millimeters of mercury. And if you remember, 760 millimeters of mercury equals an atmosphere. So when the blue line, which is the vapor pressure curve, and notice how it increases with temperature, when the vapor pressure equals the atmospheric pressure, that's where boiling occurs. And so normally water boils at 100 degrees Celsius. Technically, 100 degrees Celsius is called the normal boiling point. A normal boiling point is just when the external atmosphere is equal to 1 atmosphere. And we'll talk about this in a little bit.
In the flask is water heated to about 55 degrees Celsius, well below water's normal boiling point. We use a device to evacuate the air from the flask. The water boils, though its temperature remains at around 55 degrees.
So you can make water boil at temperatures other than 100 degrees Celsius. You just have to change the external pressure. So for example, on the top of Everest, where the pressure, atmospheric pressure is much less than 1 atmosphere, you need like canisters of gas to breathe and stuff like that. You can make water boil much less, like only 50, 60 degrees, whatever. On the other hand, if you go to places that are lower than sea level, for example, Death Valley has some places, I guess, that are lower, then you'll have a pressure higher than 760 millimeters millimeters of mercury, it would take more than 100 degrees Celsius to make it boil. So you can change the boiling points of liquids if you can change the pressure. And this is fascinating. So you can actually change the boiling points of liquid water by changing the external pressure. Kind of exciting.
Heating the liquid water converts it to a gas, which pushes molecules of air out of the container. The inverted can traps the gaseous H2O when we place the can in cold water. The temperature change converts the gaseous water into liquid water, which occupies a much smaller volume. The can is crushed by the pressure of the atmosphere.
There are some fun applications of this and some not so fun applications, as we'll talk about. At home, if you're bored one day, take an aluminum can and put just a tiny bit of water in, like maybe, a squirt or something like that, 10, 20 milliliters, and boil it over a hot plate. And what that does is it turns the little bit of liquid water you have into a gas, and then invert it into cold water, like a container of cold water, and the can will literally squish like that, which is crazy. And what's happening there is the liquid water that was inside the can has vaporized, so then you have gaseous water in the can. And when you cool it down, that liquid water quickly turns back into a liquid, and liquids don't have as much force over them, much vapor pressure. So the external pressure, which is around us on the Earth all the time, pushes itself in, squishes the can. Pretty crazy. Now, an uncool way that this is appropriate is those tanker cars there in the picture in the middle lower part of the screen. And oh my gosh, so somebody had a little bit of liquid still in the can, and they probably were washing the outside of it with water, cooling it down. And what happened is the gas inside condensed back into a liquid. The whole tanker car was squished, just like the can, because if you turn the gas back into a liquid really fast, then there's no more pressure pushing out, and it squishes it. All around us on the Earth is pressure pushing down from oxygen and nitrogen and those kind of things. And so you always have an external force, the atmospheric pressure, and an internal force. So like our blood has pressure and stuff like that. And these cans and the car are the same way. Like they had a force pushing out against the atmospheric pressure. But when the internal force was removed, i.e. gases turning to liquids, then squish, the atmospheric pressure just pushes down, squishes us. Kind of wild. Kind of cool, I won't lie, but kind of cool. And it's hopefully something that could be avoided by these people in the future. Vapor pressure, again, is the liquid over a gas, and it exists at all different temperatures. As temperature goes up, you have more vapor pressure. So here we're seeing three vapor pressure curves. On the left is diethyl ether, in the middle part is ethanol, and on the right part there is water. Now diethyl ether, the red atom in the middle there, that's oxygen. And so there's a CH2CH3 group to the left and a CH2CH3 group on the right. And if you remember, oxygen likes to have two lone pairs on it. So that oxygen right there is in a polar environment. So we would call diethyl ether to be polar, and it would exhibit dipole-dipole forces because polar things have dipole-dipole. Ethanol and water to the right also are polar. They have an O connected to different things. It's going to be polar. However, ethanol has an OH bond, so that's a hydrogen bond right there. And water also has hydrogen bonds, but water has not just one, but two hydrogen bonds, two OHs on it. So water has the strongest intermolecular forces. It doesn't have just one hydrogen bond, it has two hydrogen bonds. Ethanol is in the middle, and diethyl ether is on the far left. It has the weakest forces. And that's kind of exhibited here in these vapor pressure curves. So the red curve is diethyl ether, and it reaches the boiling point, which is where the vapor pressure equals the atmospheric pressure, which is normally 760 millimeters of mercury. It reaches it at 34.6 degrees Celsius. Ethanol, though, it takes 78.5 Celsius to get it to the boiling point, and water normally is up to 100 degrees Celsius. So what we're seeing here are a couple of things. First of all, vapor pressure is increasing with temperature, all right? All of those curves are getting bigger as the temperature gets bigger, definitely. When the vapor pressure equals the external pressure, the liquid will boil. And the normal boiling point is where you reach 760 millimeters of mercury, 1 atmosphere of pressure. So that's why the boiling points of liquids will change with altitude, because higher elevations will have lower external pressures. It's going to be easier for these things to boil. On the other hand, we're mostly concerned about the normal boiling points where 760 millimeters of mercury is met. That's why that dashed line is there at that point to show the normal boiling points. We're also seeing here how vapor pressure depends on the intermolecular forces, because diethyl ether is just dipole-dipole. Ethanol, the alcohol, has an OH bond, but water has 2 OH bonds. So water has stronger hydrogen bonds than the alcohol ethanol, but ethanol and alcohol and water both have hydrogen bonds, while diethyl ether, which is the left-hand side, is just dipole-dipole. So we are certainly seeing the effect here of intermolecular forces. The weaker intermolecular force has a smaller vapor pressure, and the stronger intermolecular force then will have a different one at the same temperature. So on the basis of the relative strengths of the intermolecular forces, predict the order of decreasing boiling points for these substances. So decreasing means strongest, the highest first, and the smallest, the weakest last. And you can see that in these examples we have CH3OH, CH4, and H2. Okay? Now, CH3OH has an OH, and OH is a hydrogen bond, so that's going to be pretty strong. CH4, the next one, is carbon completely surrounded by hydrogens. You can draw a Lewis structure. It's tetrahedral, sp3, all the things we talked about earlier. But the important part for us here, C and CH4, non-polar, so that's going to be induced dipole, induced dipole. And then finally, hydrogen, dihydrogen, is H2. That's just 2 hydrogen atoms. That's also nonpolar. All right? So in terms of just the intermolecular forces, you must put CH3OH first. It has the strongest intermolecular force. It should have the highest boiling point. Now, between CH4 and H2, since they're the same intermolecular force, put the bigger molar mass first, because the smallest molar mass should have the smallest boiling point. So CH4 is roughly 16 grams per mole. H2 on the periodic table, roughly 2 grams per mole. So my money here would be on putting CH3OH first, CH4 after that, and H2 after that. The strongest boiling point goes to methanol, CH3OH, because of the hydrogen bonds, the strongest intermolecular force. Both CH4 and H2 are intermolecular force of induced dipole. They would be the same, but CH4 should be higher. Bigger molar mass usually means a higher boiling point, so the smallest boiling point should be for H2. So the normal boiling point is where the vapor pressure of the substance equals the atmospheric pressure. And in the normal boiling point, that point would be 1 atmosphere, or 760 millimeters of mercury. You can make water and any liquid boil at basically any temperature, more or less, if you change the pressure. But the normal boiling point is where the atmospheric pressure equals an atmosphere. Liquids will boil at other temperatures by changing the external pressure. And this is just an example showing the different boiling points of water at different pressures. And wow, this is kind of cool. So there's 1,013 millibars per atmosphere. And if you look on this table long enough and you use even better sig figs than I just used, it's technically 1,013.25. And that's where the boiling point of water is 100 degrees Celsius. But scientists use water a lot, as you can probably imagine, so they will let the pressure be different, and you can see the effects on the temperature. So you start lowering the pressure, i.e. going to the left, if you will. You can see how the temperatures begin to go down. On the other hand, sometimes you have pressures greater than an atmosphere, i.e. go to the right, get numbers bigger than 101.3.25, and you can see how the temperature goes up. So there's a lot of flexibility if you can change the pressure, and using a vacuum, it's not too hard to do or anything like that.
The viscosity of a liquid depends on the strength of its intermolecular forces. Glycerol has relatively strong intermolecular forces and is rather viscous. Its resistance to flow is high. Ethanol, by contrast, has weaker intermolecular forces. It flows easily and has low viscosity.
So intermolecular forces are obviously pretty important to chemists. It helps you determine boiling points, melting points, helps you explain why some compounds boil higher and lower, stuff like that. Another use of intermolecular forces is through what's called viscosity. And viscosity is essentially a resistance to flow. So substances that are very viscous flow very slowly. Substances that have low viscosity flow very easily. And if you compare it like you did in the video there, the two compounds, glycerol and ethanol. Now, the red atoms are oxygens, and ethanol has an OH, so one source of hydrogen bonds, which is pretty strong. But glycerol is what they call a triol. It has 3 OH bonds. So you can see there's 3 oxygens, each of them connected to a hydrogen. So it has very strong intermolecular forces. So one component of viscosity is the shape and the strength of the intermolecular forces. So based on these two structures, we would say that glycerol probably will be more viscous. Those glycerol, those 3 OH bonds will connect to other OH bonds and other glycerol molecules and resist the flow. Now, in reality, viscosity has a lot of other components. It's more than just intermolecular force, but it is one of the components of figuring out when things are viscous or not. I just wanted to point out here another example of how important these IM forces can be.
A paperclip is placed carefully in water, or rather on it. The metal clip floats because it isn't heavy enough to break the water's surface tension. By adding a small amount of soap, we reduce the water's surface tension. The paperclip sinks.
This surface tension is the quality of a liquid that causes the surface layer of that liquid to behave like an elastic sheet. It's the effect that allows insects to walk on water and water drops to hold together.
Wow, that's crazy. That's amazing.
This cycle happens again and again until the droplet is small enough to be completely absorbed.
Surface tension is another phenomena that results from intermolecular forces, especially strong intermolecular forces. And water having strong intermolecular forces is a classic example. But in a nutshell, the water molecules on the outside of the liquid have a net force that kind of pulls them down. Internal water molecules don't have that, but the ones on the outside do. So it creates like a small, as they said in the video, they're kind of like elastic sheet that kind of permeates. Now, it's not a super strong sheet. So if you go swimming, you bust right through that and you go swimming. But little tiny bugs can float on the water because they don't have enough mass to float through it. And like in the first video there, you can actually place a paper clip on water and it will float. It's amazing. You have to be very careful and stuff like that, but I have done it. It's amazing. It also allows water to stay as little droplets for a long time because it holds them together until you can no longer do it. So surface tension is important. If a pollutant gets in the water, it causes chaos on the ecosystem because the insects can no longer float, they sink, all right? So that paperclip sunk when they put soap in the water. This is what happens when pollutants get in the water a lot of times. Then the insects will sink, and the insects sink and they die, then the other animals are affected, et cetera, et cetera. So you got to be careful of pollutants. But anyway, surface tension is one more thing that intermolecular forces tend to help us understand. So which of the following would you expect to have the strongest surface tension? Okay. And strongest surface tension for our purposes will be directly related to the intermolecular forces. So of those molecules listed there, you want to look for things with a bigger intermolecular force. And again, the punchline, you can probably imagine, we're going to be looking for hydrogen bonds, all right? Because things with hydrogen bonds are super strong. If you have have an oxygen, nitrogen, or fluorine connected to hydrogen, you'll have a hydrogen bond. So that first one there, CH3, CH2SH, the sulfur is polar. Sulfur, like oxygen, will have two lone pairs, but sulfur is connected to hydrogen, but sulfur's not nitrogen, oxygen, or fluorine. That's not going to be as strong. It's going to have dipole-dipole forces. B is another example. The oxygen is connected not to the hydrogens, but to the carbons. If you can draw the Lewis structure out, you can confirm this. So oxygen connected to carbon is not hydrogen bonds. That would be dipole-dipole. But C, that oxygen with CH3CH2OH, that oxygen has a carbon to the left and a hydrogen to the right. So that has the OH bond. So that's going to be pretty strong. That's going to be dipole-dipole plus hydrogen bonding. And again, you can only have hydrogen bonding if you have N, O, or F connected to hydrogen, and that definitely does. Now, answers D and E are similar. You've got a sulfur or an oxygen, but neither one of them are connected to any hydrogens. You would just have them connected to carbons, so D and E would be dipole-dipole. So the strongest of all of those will definitely be C, hydrogen bonding, all right? And it's really important to chemists, society, and life, and all this kind of stuff, so I keep talking about it here. You want to find N, O, or F connected to hydrogen. The strongest bond is the result of a lot of these things that we're talking about. Intermolecular forces also create what's called capillary action, or are responsible for it, whatever you want to talk about it. Cohesive forces are interactions between like particles, and adhesive forces are interactions between unlike particles. And adhesive forces, unlike particles, can lead to what's called capillary action, all right? I'm not going to ask you to ever define cohesive or adhesive, but I do want you to know about capillary action. Because if you look, for example, at a 10 milliliter graduated cylinder and you fill it up with some water, you'll see kind of a dip in the meniscus, like the top of the liquid. Now, the dips that you'll see will either be concave or convex, all right? And in a concave meniscus, you usually will have things like water on glass. Now, glass is essentially then a type of silicon oxygen system, and silicon oxygen is a polar system, and polar glass will get along with things like polar water. So concave is an example of something you'll see. You'll see a concave meniscus when you see water in most glassware. So on the left-hand side, that's a concave, all right? Like you can see, it's kind of got like a dip to it, all right? That's what happens. Now, if you ever want to see a convex meniscus, which is the opposite of what you see with water, you actually see a bulge in the middle, and that's because those atoms are trying to get away from the glass, all right? So mercury is a good example of that. Mercury is basically a metallic substance. Metallic substances and polar things don't necessarily get along together. That's going to create a convex meniscus. So polar things usually create concave meniscuses when they're in glass, and nonpolar or metallic things will usually be convex. Now, concave up is like a cup, and concave down is like a frown. These are expressions that people have told me about in the past. Maybe they'll help you understand it, maybe they won't, but at least you understand now why you're seeing concave or possibly convex meniscuses. Guess what? Intermolecular forces once again.
When a piece of paper is dipped in water, the water moves up the paper by capillary action. The attraction of the water to the surface of the solid paper allows the water to rise against the force of gravity.
If you've ever had a newspaper and you got the newspaper wet, the water kind of spreads over the newspaper. It doesn't just stay where it is. This is also capillary action. Paper, like glass, is usually made of things that are polar, all right? And the polar things and water get along really well. So water just starts going all over the place. Chemists use this in what's called chromatography to separate and identify certain substances. And this quarter, we might see the chromatography lab, which we'll talk about this in more detail. Guess what? Intermolecular forces to the rescue. Oh boy.